So, let's kind of continue through with this, right? Did you guys get a chance to finish this up? For the most part? Okay, so let's just kind of keep going through this then. So the limit, and by the way, this is also a very important skill that we need to have. So I'm not actually giving you a function here, I'm just giving you a picture, and we must be able to evaluate this limit, evaluate these things based on just looking at a picture here. Okay, so let me review real quick. So the first one, letter A, we asked to evaluate the limit as x approaches -2 of the function. Okay, and so if we go here, here's the x value of -2. But I'm not trying to approach here, right? I'm not trying to approach here. My function, where is it? My function as I approach -2 is like going this way, right? It's going up, 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 up. I'm getting, my x values are getting closer and closer to -2. Likewise, from the other side of x equals -2, my function is approaching from this direction. And so we said in the limit, what it's approaching, what's the y value we are approaching here? It's 3, right? As we move along to as we move from left to right, closer to that -2. As we move from right to left, closer to that -2. Both sides are approaching 3, so we say the limit is 3. Okay?
Well.
Okay, and so then let's see here. F of -2. Now the function value at -2. It's not 3. How do I know it's not 3? Open circle. So we keep going, and at -2, the value of the function is 4. Yes, that little dot counts as being part of the function because it's graphed that way. Okay. Next one, then, the limit as x approaches 1 of the function. We have a volunteer. What would that be? So, yeah, Brandon.
1.
It would be 1? As we approach, as 0, right? It's 0, yeah, it's approaching 0 there. Okay. And what about f of 1, Ryan?
Would be 0.
It would also be 0. Okay. So in this case, the limit and the function value at x equals 1 are the same. In A and B's case, the limit and the function value are not the same, right? Remember I gave you that like super starred statement in the notes that said like just because a function exists at a certain point does not mean the limit exists. Like the existence of a limit and the existence of a function at a point do not depend on each other, okay, necessarily. All right, and then lastly here, the limit as x approaches 3. What would we say there? Any idea? Yeah.
Doesn't exist.
Awesome. Yeah, it doesn't exist. How do you know it does not exist?
Well, at one end it's approaching negative infinity, at the other end it's approaching infinity. That's their approaching same number.
Right, it's got to approach the same number. So if they both approach positive infinity, would we say the limit exists? No, still not. Anytime a limit approaches infinity, we say the limit does not exist. You can put a DNE there if you want to.
So it has to like look like it hits a number.
It's got to, yes, it's got to have a limit, right? It's got to have a stopping point. Infinity has no limit; it keeps going, and so that's why we don't really count it as being a limit value. And then f of 3, what would that one be? What we say there? Yeah, Ryan, what do you say?
Undefined.
Yeah, undefined. Again, why? What indicates that?
Because there's nothing.
Right. Well, there's an asymptote, right? It looks like so we are undefined there. Okay, there's no given value. Okay, so that's that. And I think in the homework I gave you some like examples, some like extra practice of that. I think so. Okay. All right. Very good. So that being said, let's get into what we're going to do today, and I think we should have enough time to get it all done. I hope so. Okay. So let's continue on with limits here then. So we're going to, and if you want to just continue on that page, I'm going to, so why not, right? So evaluating limits analytically. So you must be able to evaluate a limit using a table, like you did in the homework. You must be able to evaluate a limit using a graph, like we did here, also like you do with your graphing calculators. And thirdly, you must be able to evaluating limits analytically. English is my second language, I guess. Here we go. Okay, evaluating limits analytically. That's the third way we need to evaluate limits, is analytically. Okay? So, in some cases, I'll just go ahead and scoop this up. In some cases, limits can be evaluated by direct substitution. Okay. Did you guys get to this in pre-calculus?
Yes.
Okay, you think so? And maybe once you see it, it'll make sense. Okay, this is what Don was talking about last time. Okay, direct substitution. Okay. In fact, the limit as x approaches c of f of x, okay, does equal f of c. Okay, now I just got done telling you that the existence of a limit does not necessarily mean that the function is also exists at that point. But now I'm telling you that's not true. I'm telling you that the limit as x approaches c of f of x is equal to f of c, with a condition. If and only if, yeah, IFF, yeah, exactly right, f of x is continuous. Okay, is continuous. We'll define continuity later. Okay, right now you guys kind of have like a conceptual understanding of continuity, right? So for example, if I scoot back up here to this previous graph, is this graph continuous everywhere?
No.
How do you know?
There's an asymptote.
There's an asymptote, right? We have to like jump here. If I were to like, the way I kind of would teach my Algebra 1 students when I would teach continuity to them, I'd be like, if you have to pick your pen up at some point when you're tracing the graph, that means your graph's not continuous. Okay?
Does that mean that even if the asymptote wasn't there because of the dot?
Yeah, so even if we had not this part, this is a discontinuity as well. Exactly right, Caleb. So, that's why then, in this case, the limit and the function may have different values. This thing is not continuous. Therefore, the limits and the function values may be different. If your function is continuous, then you can go ahead and just plug in your limit value, and that'll give you what your function value is. The limit and the function value will be the same thing. Okay, they will be the same if your function is continuous. If it's not continuous, then you result in the different answers here. Okay, like we have. All right, so let me show you some basic limits. And this is a theorem. These were proved by somebody smarter than I. Okay, so we'll look at some basic limits. Okay. So we're going to let B and C be real numbers. Okay, this is our setup here. And n, I'm going to use like a little cursive n there, be a positive integer. Okay, so and I realize maybe we've lost some people here because when we say real numbers, what do I mean by real numbers? So yeah, not imaginary, right? So what numbers are included in real numbers?
Anything more than a square root of a negative or infinity.
So right, anything that's not the square root of a negative. So like something like pi, that's real. Okay, that's one of those numbers that like goes on, like its decimal goes on forever, never repeats, and so you can that's an irrational number, but it's counted as a real number. Okay, that also counts like numbers 2, 3, 4, 5, 6. It counts all fractions and stuff like that too. And then n is a positive integer. Now what are integers?
1, 2 digits.
Positive, negative, just like whole numbers basically. So like the positive whole numbers, right? And then you like their negative version. So like 1, 2, -1, -2, not -1/2 though, right? So just to clue you in there. Okay. So then these things are true. The limit as x approaches c of a plain old number b is just going to be b. Okay. The limit as x approaches c of x, well, what should that be? It's going to be, if the limit as x approaches c of x, that should just be c. Yeah, we're approaching c, so it's just going to be c. Direct substitution. And then the third one here, the limit as x approaches c of x to the n, what will that be? Again, if x is approaching c,
C to n.
c to the n power, that's right. Okay? Now, some of you guys are probably looking at this like, Mr. Wood, where are the numbers? These are all letters. Well, B is representing a real number. C is representing a real number. We're just trying to be very generic here. But this is part of calculus, is some of these letters. Now, don't worry, I'm not going to leave you high and dry here. We'll look at some examples, put some numbers in so you can get more comfortable. Okay? And, well, we'll do these together. I was going to have you try them, but we'll just do these together for the interest of time. So let's find the limit as x approaches 2 of 3. Okay? The limit as x approaches 2 of 3 is... It's 3. It's 3. Okay? There's no... So again, remember, our first tool, now that it comes to evaluating limits, our first tool we want to use is direct substitution. Is there any x in here for me to plug that 2 into? Is there an x in here? No. So this fact that x approaches 2 of 3, who cares? It's got to be 3, okay? If the limit as x approaches pi of 3 is 3. The limit as x approaches 100 of 3 is 3, okay? It doesn't matter, there's no x to plug into there, okay? But, let's say I have the limit as x approaches negative 4 of x. The limit as x approaches negative 4 of x. What's it going to be? Negative 4. Direct substitution, right? We can just, so if x is approaching negative 4, x is going to be continuous, so we can just go ahead and plug in the graph of x as continuous, right? It's just a line. It's a line with a slope of 1, so it's continuous. There's no problems there. We can just direct substitute it in, no trouble.
So if it was 2x, would it be negative 8?
If this was a 2x in here, it would be negative 8, yes. Now, we haven't talked about that property yet, but yeah, you're right. Okay, and the last one here, the limit as x approaches 3 of x squared. What would that be? 3 squared or 9. 3 squared or 9. Either one's acceptable there. Okay, questions on any of those properties? Does that make more sense now that there's numbers in there? You're welcome. Okay, you're welcome. I know. I hated it too. My calculus teacher would put those stupid... And then in college, they started using all those Greek letters, and I was like, all right, I don't even know what this letter is or how to write it. Now you're making me draw this. All right, theorem. More properties of limits.
Like back to Mr. Biggs class all over.
Is that right?
Yeah.
Sorry,
Geometry.
am I giving you nightmares? All right, let B and C be real numbers again. Okay, let N be a positive integer. And let F and G be functions with the following limits. Okay, I know, I'm sorry, I'm getting ahead of you here, but I'll slow down here and give you a chance to catch up. Okay, so the limit as x approaches C of f of x is L, and we'll say the limit as x approaches C of g of x is K. Bless you.
Thank you.
Okay. So all that's set up, and now we're going to use those to get some, to develop, or to indicate some properties, show some properties here, okay? So the limit as x approaches C of f is just L, it's some number L. The limit as x approaches C of G is some number K, okay? So they don't necessarily approach the same thing, but they do approach a number. They do have a limit, a value, okay? So first kind of property here is the scalar multiple. So this is kind of what Ryan was talking about earlier. Okay, you don't necessarily need to know the name, but the property is important. So for example, the limit as x approaches c of b times f of x. Okay, so you've got your function here, whose limit you know, and then we put a number out front. Ryan put a 2 in front of our x, right? And so it's just equal to then that same b times what your answer was, b times L. Okay, so if as the limit as x approaches c of f is L, then b times f of x will just be b times L. You just multiply by the number there. Okay. Additionally, we have a sum and difference property. So for example, the limit as x approaches c of f of x plus or minus g of x. Okay, so now we've taken those two different functions and added them together, or subtracted them. That's going to be equal to then just the sum or difference of their answers, of their limits. Okay. So you can break up limits over addition. You can break up limits over addition. So if you don't want to take the limit of the whole thing, you can take the limit of a piece and then add the limit of the other piece, and that'll still be correct. Okay? Product. Okay? So same is true for a product. You can break a limit up over the product. So if you have the limit as x approaches c of f of x times g of x, what can we say that equals then? L times k, exactly right. L times k, okay? So L times k. All right, 4, guess what? Quotient. Also works. The limit as x approaches c of f of x divided by g of x. What should that equal? Yeah, so which one is it? F approaches what? L. G approaches k according to this, so it's going to be L divided by k. We have to have one little caveat here. K cannot equal what number? 0, okay? So your limit would be does not exist then if the limit there if the k is 0. Okay, and then the power rule, which is very similar to the one we kind of talked about earlier there. But if you have your function and your function is raised to the power n, okay, what do we want to say that should equal then? L to the n. Okay, very good. So, let's see some examples of that. So, our directions here, we're going to try an example. Okay, we're going to use the properties. Scoot up here. Use the properties to find each limit. Okay, so letter A. I'll do one and you'll do one. Well, we'll do one together and then you'll do one. Okay, the limit as x approaches 2 of 4x squared plus 3. Okay, so how can we evaluate this? What do I actually have to do? Plug it in. Plug what in? Yep, just plug the 2 in. 4x squared plus 3 is a continuous function, right? There's no issues, there's no problems here. They're not going to divide by 0 or anything.
Please pardon this interruption. Teachers, at this time, if you could please dismiss seniors to the auditorium. Seniors, when you arrive in the auditorium, please form 2 lines down the center aisle. Thank you so much.
So we get 19. Okay, Nate, the rest of this will be on YouTube if you want to check out the rest of it, but I think you know, if you need to. So I used a couple things here. Basically, we're using direct substitution, but yeah, it kind of so basically, you can kind of think of it as yeah, we're plugging in the 2 for x, we're evaluating the x squared, then we're multiplying that limit by 4, and then just adding 3 to it. But ultimately here, what we're really doing is we're just plugging it in. That's all you really have to do, okay? All right, so you guys try the limit as x approaches 1 of negative x squared plus 1. Okay, and so volunteer. What we come up with? Anyone want to volunteer answer here? Some besides Ryan or Brandon to give us some variety here. All right, Tyler, go for it. 0. That's right. Sorry, guys. Thank you for being willing to volunteer. Okay. So again, if you really want to break this down using your rules, you don't have to do it this way, but if you really want to break it down, here's how we can rewrite this. I can write this as the limit as x approaches 1 of negative x squared plus the limit as x approaches 1 of 1. Okay? And if I really want to break this one down further, I can put a negative in front of that limit and make this just x squared and then limit as x approaches 1 of 1, right? And now I can do the direct substitution, which makes it 1, but a negative 1, and then that makes it 1, and then makes it 0. Right, that's a lot of work, but I'm just trying to show you very explicitly the properties there. Absolutely, yep. But I'm just trying to show you very explicitly using all the properties and stuff like that, how we're kind of taking advantage of that. Okay, and I have one more little thing here, example, and then I'll give you the homework, and hopefully that'll be able to squeeze it in here. I think I can. Okay. So here I've got, if the limit as x approaches c of f of x is 3, notice I'm not giving you f, and the limit as x approaches c of g of x is 2, find, and I'll write a problem up here. Okay, so we're not told what these functions are, but we are given information about what their limits as x approaches c, what the limits are as x approaches c. Okay, so using our using our properties here, what do we really need to do here for letter A? Yeah, so what is the limit? What's going to be our answer here? Just 8. G of x goes to 2, so 4 times g of x using that scalar multiple property. 4 times 2 gives you the 8. Okay. How about the limit as x approaches c of f of x plus g of x? What will that be? Yep. Yeah. The brackets are just there for grouping symbols, that's all. So you could use parentheses if you wanted to, but I like to use brackets because we're already using the parentheses with the functions. So what would the answer be, by the way, Anna? Yeah, 5. Good job. Okay. All right, one more here. Oh. Sorry, I meant to do one more. I know, all right. Mr. Wid. All right, limit as x approaches c of 2 bracket f of x minus 3 parenthesis g of x squared. Huh. So this is kind of using like almost all of our properties here. Okay. All right, so what do we think here? Some people still working, maybe? I'll give you a chance. So, hold on, one more minute. We'll go over it. One more minute. Oh, crap. Hey. So, Emma, what do you say? You got it, Emma. Good job. Negative 18 is our answer. Okay? Questions on any of that? Okay, so we'll hold off on going on any further there. And your assignment, let me get that. Okay, your assignment for tonight. Oh, this is great. It is page 75 to 78.
I mean, I know.
Numbers 18 to 28. All. Okay. 31, 33, 66, 73, and then 75 to 78. Okay. The 18 to 28 part is mostly just evaluating limits. I will say that 28 has parts A through H, but I'm sure they will be really quick parts. I don't really have a whole lot of work shown here. But 28 has an A through H.
Really?
That's right, okay.
That doesn't,
So,
that's like another, that's like telling us it's only 5 problems, but it's really being like 15 problems.
but I promise they will go fast. You'll look at these, and you'll think, why did I complain to Mr. Whitmire? Those were so easy. It's these I should have complained to him about. The last ones, not these early ones. Okay? Yeah, there's some true false stuff in there. I have a bunch of geometry students coming in today. So if you want to come in, that's great. But they have a test tomorrow, and they're all excited. But then Friday, I can definitely pull you in Friday, Max. Okay? Mañana. Yeah, I got 14 kids coming in.